So, hello, good evening. My name is Rui, and I'll try to keep this short because I guess everyone just wants to go and have dinner and a beer. I sure do. So, actually, some of the issues that were discussed during the Q&As from previous presentations were the topic of my thesis, which is the enrichment and the creation of IoCs of quality out of OSINT. It was my master's thesis. Those are my advisors. And I did it in the University of Lisbon. Why do we care about this? Because the same reason why we know we will not get out of a job in the near future, it costs a lot of money. 4% of global GDP next year is expected to be lost to cybercrime. And why does this happen? Two reasons. We're working against people that are highly focused and highly dedicated to what they're doing. They see that the return on investment has a lot of potential, and they also are using new ways of attacking, which also increase the difficulty that we have in combating these threats. So, where are we? We started by having no defenses whatsoever. In the beginning, the internet was something that was supposed to be for sharing, and no one even considered the hypothesis of its being misused. We understood the error of our ways, and we started installing perimeter defenses. The problem with the perimeter defense is if you build a wall, if someone manages to cross that wall, you don't have anything else. So we moved to in-depth defenses, which works fine until you find an adversary that is capable of adapting to what you have within your network and you will change the way he is attacking to adapt to what you're monitoring. And so we moved to dynamic response defense, which is three things: advanced malware detection, event anomaly detection, and what brings us all here, intelligence-driven defense. And that's where we decided to work. So where are we now in this field? We moved from manually sharing our knowledge to creating platforms to help us share the knowledge. However, and most of you are surely aware, there was a report by ENISA in the beginning of this year which criticized the initiatives, not in the sense that they weren't needed, but in the sense that we still have a lot to work until we get to a place where we can be comfortable with the effort we're putting into this field. And so they indicated a lot of issues that appear. First of all, we have a high volume of information that is shared, which makes it hard for people to understand what they're seeing and to get the information that they need. Furthermore, we don't have common sharing standards. We have certain standards that are more used than others, but we should move towards something that is everyone agrees it's the way to go, and we all use the same standards. Instead of having, in my platform, I have to have a converter. At the end, I have to have other converters so that I can receive input and then output the information for something that other people, can use. And we are collecting data. We're not doing intelligence. This is a very serious issue because collecting data is not the same as creating intelligence. Creating intelligence is answering a question that you need to have answered. Collecting data is just hoarding. And that's what most of the platforms are currently doing. We're hoarding data, but then we have a hard time making it into something useful. So out of these issues for the thesis, we had to choose something to focus on, and we decided to focus on three challenges. First, we wanted to reduce the quantity of information that reaches the analysts. We don't want the analyst to have to sort through all the information that is receiving on a daily basis. If we consider that there are tens of thousands of new malware samples that are detected daily, it's impossible for a human being to deal with that kind of information. Second, we want to increase the quality of the information that is being shared, or of the intelligence. This means four things. We have to reduce the timeliness, the time between detection and the information actually reaching its goal. So the information analyst, the security analyst, or the systems that are defending our network. we have to guarantee that it's both accurate and relevant. So we have to guarantee that the information that we are using actually has some answers or needs, and it's not, if I work in a bank, and I actually do, I don't care about the threats that affects like the navigation systems of an airplane. I just care about threats that will impact on what I have within my network. And finally, completeness. And here it's something that it was approached in the last talk in a sense, which is if we use different names when we're analyzing a different same sample, when we reach the end, and if I'm analyzing the network part of the malware and someone is analyzing the system part, we'll reach two different IOCs that won't be related, and in the end, maybe they are in my database, both of them, but I'll lose part of that information because they aren't connected. And finally, automation is key. We don't want to lose time having someone to have to work on that information. We want to have something that we let go, we configure it, and after that, it's just running on our system and completing it. So we looked at MISP as a solution to start implementing our solution, and what we found is new events can be duplicates, which means it increases the storage requirements and it's information that's not useful to anyone that we're storing there. Second, MISP creates direct connections, which means, and we've seen multiple representations during the day, you have an event, you see all the events that share attributes with that one. What if the next one on that level is something useful to us? You would have to go manually or lose the information, which means that you're either losing time or losing information. So we try to resolve this situation. How? First of all, we consider clustering and aggregating information that is related to one another, so as to create a new enriched IoC, which brings all the information that is connected into a single report that will reach the analyst. This means working at two levels of the architecture. We have to work in the configuration of the threat intelligence platform, which means we have to know what we want to answer so that we make the correct choices when preparing our platform to answer them. And second, we have to work in the internal processing capabilities, which is the platform needs to be able to do this operation by itself instead of doing it instead of the security analyst doing it. So then, lastly, automation by design, which is basically something that is a pre-requirement for anything we do. So we designed this solution. We have the sources, which should be focused on threat feeds that matter to us. We have a layer of other threat intelligence platforms to try to use what they bring to the product. And by this I mean, for instance, using IntelliMQ to enrich IPs and DNSs, so that when we have the information reaching what we developed, we have hooks. And hooks here are information that will allow to create connections to other events that we have in our database. And we created two modules. The duplicator module, which, as the name indicates, allows to eliminate information that serves no purpose because it's a duplicate, and a correlator module, which has an aggregation part and a representation part to create the enriched CIOCs. So how does a deduplication work? We considered an event as a set. And if we consider an event as a set of attributes, you can use set theory to compare two events and to decide which one you should keep. This means that you have to have criteria, and the criteria are found within the metadata. So you'll see, for instance, if you have two events that have the same information, you'll see if one of them has already been validated by a human, so if the trust level is higher, you can consider that that one is more valuable than the previous one, which was still hadn't been analyzed, and so forth. Regarding aggregation methods, we we defined two methods. One of them is closer to what MISP has, which is the naive method. And we basically focus on the naive method on direct connection. So we look at an event, we see if it shares attributes with other events, and then we take that group of events as a cluster and a potential new enriched YOC. This has a problem. An event can appear on multiple clusters, which is logical. We have another alternative, which is the n-level aggregation. In the n-level aggregation, what we do, and similar to what you were doing, is we create a graph where the nodes are new events, or all the events in our database. We then look at shared attributes to create edges, and we set filters to allow only certain edges to be created, and then we identify all the subgraphs, and those subgraphs will form a new enriched YOC or a new possible enriched YOC. Just an image to give an example. If we are using the naive approach, consider that we have these events in the database. When we look at the first event, it shares one attribute with the second, one enriched YOC. We move to the second, another enriched YOC, another enriched YOC, and so forth. If we move to an n-level aggregation with the same, using exactly the same database, we will first create the nodes, represent the nodes. We would then, for each relation, create an edge. And finally, we would identify all the subgraphs that exist. In this case, we have two. And these two would be possible enriched YOCs. So we needed to make a proof of concept. So we developed in Python 3 over a MISP installation. We focused in these two modules. So we basically used everything that we could use out of MISP so as not to lose time. I didn't have that much time to develop, so it was basically get the most out of MISP. And we made the implementation to allow two choices. The first one is we could choose subsets of YOCs that are in our database and use them as do the selection that way. While at this time we were just working in a proof of concept, so we didn't have a specific target. In the future, this would allow, if we want to focus on specific sectors or in specific threats, we can select only those YOCs that are in our database that relate to that issue, instead of losing time analyzing all the database. Then we also made valid relationships, so we set different filters that could be used to make the creation of the enriched YOCs, and we made two important assumptions. The first one is trust level correlates to quality, which means that we are trusting the other participants that contribute to our database, that if they set a trust level at 2, they did their job, and that the quality of the information of that event is actually better than another event that is in the network without having been certified, and that blacklists are correctly tagged. This is extremely important, and blacklists aren't the only case. There are other types of events that appear that can mess up the way we're doing things, because if you have an event that creates relationships that aren't indeed useful, it will create an enriched YOC that has no value. So if you have a blacklist, it will bring events from different incidents, because some of them only list IPs without caring if they are related to a single threat, and they will agglomerate everything around them, and it's a mess. So we selected an experimental set. We opened 34 feeds from 12 organizations, collected 1,174 events. Most of them, as you can see, are of a high trust level. So in our vision of the world, they actually have high quality. And we ran our platform on that data set to see how it would work. And so we selected a subset. Only those with a trust level of 2 were selected, and we eliminated all those that had a tag of blacklist. And we said, okay, let's see, with all the filters that are currently connected, how does it work? And as you can see, there are two factors here that are important or that are interesting. As the filter goes deeper in detail, you reduce the number of potentially enriched yolks that you have, which makes sense because you allow less connections, and the connections that you allow are those that interest you the most. And if you use the naive approach, you get a lot more potential enriched yolks than if you use the cluster approach. So after doing these first experiments, we focused on the cluster approach with the most restrictive filter. And what we got was this. We found 11 potentially enriched yolks, which we then manually went through their components, and they make sense. And here it makes sense because it's the data sets is still not. We needed a bigger data set. We needed to evaluate this in a different way. We have developed metrics like you did to try to make sense of the information and try to validate what we have, but it's still an ongoing process to be able to relate for certain the relevance of these enriched yolks. And actually, you'll see that that's a work that is currently being done. So this is a representation of what we got when we represented the graph, and we're going to look just at the details of one of them. So this is the enriched yolk 9. It's composed of 7 different events that are all related or mostly related through this vulnerability, and another one appears related through this vulnerability. The filter we were using was if the events shared vulnerability or attackers, so to bring forth something that made more sense and could be more useful. And so here we have the list of events that composed it. Not very interesting. One interesting factor is, and that's something that has appeared in the literature, is you can see, if you look at this kind of data, you can see the evolution of a threat, or in this case, for instance, the evolution from 2014 to 2016 of a vulnerability over time. Who used it, when, why, to attack who. So this sort of information at the strategic level, we are already getting something that is useful. But now at the tactical level, where we're going to use these yolks to inject into a defense network, still needs some working to do just to be sure that when we create rules, we are actually creating rules that are useful and not just cluttering the system. So, conclusion, we created a new system to create intelligence out of OSINTs. We defined 2 methods to correlate and aggregate threat intelligence. We developed the platform that proves that the methods sort of work. And we did an experiment that showed that our proof of concept was working. And as I was saying, currently this was worked within the project of DCM, which is a European sponsored project. And we're working with a partner to evaluate the risk score of the detected yolks. And thank you. So repeating the question, if I understood it correctly, is if the approach we're using is not counterproductive in the long run because we're limiting the access of the information. And it's a good point. The one you make, it's a good point because indeed it can happen, and even if it doesn't, and when it happens, like, you could have had the information in the past, but this is still, like, this is the beginning of doing this. When part of the problem with this issue is, for instance, for threat intelligence quality, there is nothing to quantify it. I've looked for it because it should be something that you should be able to quantify, but it's something that it's on a case-by-case basis. And what you're saying makes sense, but what I can say is it all depends on the configurations, and that's why it's so important at the beginning. I'm not saying that you're wrong. You're absolutely correct that you should have the best database possible. The idea is to only get the information that matters at that moment to the people that are working, because you can always have that in storage. You can accumulate whatever knowledge you think will be useful in the future in your storage, and then use it to process it later on. Because the idea is that this will work automatically. So currently it's on I need to run the platform basis, but it was created and I designed it so that you could put it as a thread, and it will basically be running over and over on your database and checking for the creation of new enriched IoCs or potentially enriched IoCs. And yes, currently I have a concern about false positives because we don't know what a false positive is. So if you don't, we got 11 potential enriched IoCs, and that's, for me, and it's an issue that I have with for instance, with my advisors, because for them it's, yeah, you created these enriched IoCs. No, I created 11 events that have the information from other events that should be correlated, but there is no way to be certain at this point that they are actually, what we've created is better than what we had in the past. And so it's, right now we have the proof of concept and we created something. The future is with the risk score, seeing if that something that we're creating has added value, and we can see with the human eye some added value, because you can see, for instance, different vulnerability that reappears over time, which would probably not be that easy to detect. You can create other, like we created measures to see how a different an event evolves over time. So you can get those metrics, but this is the beginning of a new age. More questions? No? Thank you.